the Upflow anaerobic sludge blanket, septic tank, and anaerobic lagoon. The Upflow anaerobic sludge blanket reactor is widely used by biological wastewater treatment technology, particularly for treating industrial and domestic wastewater. It is designed to degrade organic pollutants through anaerobic digestion, a process that takes place in the absence of oxygen and relies on the activity of anaerobic microorganisms to break down organic material. In a flow anaerobic sludge blanket reactor, wastewater flows upward through a dense blanket of anaerobic sludge microorganisms. As wastewater passes through the sludge, the organic pollutants are digested by the anaerobic bacteria, converting them into biogas, mainly methane and carbon dioxide. The system is divided into three zones, namely sludge zones located at the bottom, activated sludge blanket at the middle, and gas liquid solid separator at the top. In sludge zone, where the sludge settles and grows, the anaerobic bacteria from the sludge blanket, which is responsible for breaking down the organic compounds in the wastewater, while in active sludge blanket, as the wastewater flows upward, it passes through the sludge blanket. Here, the microorganisms convert the organic material into biogas and biomass. The sludge remains suspended due to the upflow of the water. In gas liquid solid separator, the three-phase separator ensures that the biogas treated effluent and any solids are separated. The biogas is collected and removed from the reactor, while the treated water overflows for further treatment or discharge. The Upflow anaerobic sludge blanket reactors are used for industrial wastewater treatment. They are commonly used in industries like beer, sugar mills, palm and paper, distillers, and food processing. Key processes of Upflow anaerobic sludge blanket are anaerobic digestion and biogas production. The key biological process in Upflow anaerobic sludge blanket reactor is anaerobic digestion, which consists of four steps, which is hydrolysis, acetogenesis, and methanogenesis. The process begins with breaking down complex organic material into simpler compounds, which are eventually converted into methane and carbon dioxide by metagenetic bacteria. In biogas production, the end product of anaerobic digestion is biogas, a mixture of methane and carbon dioxide which can be captured and utilized for energy generation. And these are the advantages of the Upflow anaerobic sludge blanket reactors. It generates energy. One of the major benefits of Upflow anaerobic sludge blanket is the production of biogas, which can be captured and used for energy production, reducing the overall energy footprint of the wastewater treatment process. It is cost-effective. Since anaerobic digestion doesn't require oxygen, the Upflow anaerobic sludge blanket reactors are typically cheaper to operate in the long run due to the lower energy demands and the potential for energy recovery through biogas utilizations. It has also a minimal produced sludge. Anaerobic processes generate significantly less sludge than aerobic processes. This reduces the cost and environmental impact to sludge disposal. Lastly, it has a high organic load capacity. The Upflow anaerobic sludge blanket reactors can handle high-strength wastewater with a high concentration of organic material, making them particularly useful for treating industrial wastewater for sectors like breweries, food processing, and pulp and paper industries. However, there are also disadvantages of the Upflow anaerobic sludge blanket reactors. First, it requires a long start-up time. The Upflow anaerobic sludge blanket reactors require a long start-up period to develop a sufficient biomass concentration for effective treatment. This is especially true for reactors treating low-strength wastewater. Also, it is temperature sensitive. The Upflow anaerobic sludge blanket reactors operate best in mesophilic or thermophilic conditions. At lower temperature, the anaerobic digestion process slows down, reducing treatment efficiency. Also, it requires pre-treatment. High concentration of suspended solids, fats, oils, and grease in the effluent can negatively impact the performance of the Upflow anaerobic sludge blanket reactor by clogging the system or hindering microbial activity. As such, pre-treatment may be necessary. Also, it has a low nutrient removal. The Upflow anaerobic sludge blanket reactors are effective at removing organic pollutants, but are less effective at removing nutrients like nitrogen and phosphorus. Additional treatment processes may be required to meet effluent discharge standards. Lastly, it is potential for odor generation. Anaerobic digestion can produce odorous compounds which, if not managed properly, can cause environmental and community concerns. Let us move on to the another type of wastewater treatment under anaerobic processes, which is the septic tank. A septic tank is a widely used decentralized wastewater treatment system, primarily in areas where a centralized sewage system is unavailable or impractical. Septic systems are common in rural and suburban areas and provide an effective means of treating household wastewater. The design, operation, and maintenance of septic tanks are simple but crucial for their proper functioning. A septic tank is a watertight underground container made of concrete, fiberglass, or plastic. Its primary purpose is to separate and partially treat the solid and liquid portion of household wastewater. The process in a septic tank is mostly anaerobic, meaning it occurs without oxygen, leading to partial decomposition of organic material. The basic function of the septic tank is to separate solids from the liquids, break down organic matter, and to allow treated effluent to flow into a drain field for further treatment. The system comprises the following components: the inlet pipe, septic tank itself, the outlet pipe, and the drain field or the leach field. In the inlet pipe, the wastewater from the household, including water from sinks, toilets, showers, washing machine, etc., enters the septic tank through the inlet pipe. This flow is typically gravity-fed. In septic tank, once the wastewater enters to the septic tank, it separates into three layers. The scum layer, where fats, oils, and grease floats to the top. The effluent, where the partially clarified wastewater sits in the middle, and the sludge layer, where heavy solid waste, such as human waste and food particles, settles at the bottom of the tank. Anaerobic bacteria in the tank break down some of the solids, reducing the overall volume of sludge and converting some of the waste into gases such as methane and hydrogen sulfide. In the outlet pipe, the effluent flows out of the septic tank through this pipe. This is usually located near the top of the tank. It prevents solid waste from leaving the tank and entering the drain field. In the drain field or leach field, the effluent flows into a series of perforated pipes buried in the trenches filled with gravel. The wastewater slowly seeps into the surrounding soil, where it is further filtrated and treated by natural biological processes. The soil and its microbes help remove pathogens and organic matter before the water reaches groundwater. Septic tank treatment occurs physical separation, biological treatment, and soil filtration. In physical separation, the septic tank relies on the gravity to separate solids from liquids, while in biological treatment, anaerobic bacteria decompose organic material in the septic tank, but the only partial treatment occurs within the tank itself. In soil filtration, the final treatment occurs in the drain field, where soil filtration and microbial action further clean the wastewater. These are the advantages of septic tanks. First, it is cost-effective. Septic systems are generally less expensive to install and maintain compared to a centralized sewer system, especially in rural areas where connecting to a centralized system may be impractical. It is low energy use. Septic tanks operate through gravity flow and natural biological processes, requiring little to no energy for a day-to-day operation. Unlike wastewater treatment plants, they do not need electricity or mechanical processes to primary treatment. Third, the design is simple. Septic tanks have a relatively simple design, which makes them easy to construct and maintain. The lack of moving parts also reduces the likelihood of mechanical failures. One of its advantages is environmental benefits. Properly functioning septic system can help recharge local groundwater supplies as the treated effluent percolates through the soil. They also reduce the need for extensive sewage infrastructure. It is also decentralized system. Septic tanks allow for decentralized wastewater treatment, reducing the burden of large centralized wastewater treatment plants and supporting the management of wastewater in areas with dispersed populations. However, septic tank is known for its disadvantages, first of which is limited treatment capacity. Septic tanks provide only partial treatment of wastewater. They are effective at settling solids and reducing some organic material, but they do not fully remove pathogens, nutrients like nitrogen and phosphorus, or contaminants like chemical and pharmaceuticals. Also, another disadvantages of septic tanks is soil dependency. The effectiveness of the drain field depends heavily on soil type. Sandy soils may allow wastewater to percolate too quickly, while clay soils may not allow adequate percolations, leading to system failures. In areas with high water tables or poor drainage, the septic system can malfunction, leading to contaminations of groundwater or surface water. Another disadvantage of septic tank is the maintenance required. Septic tanks require regular maintenance, including pumping out the tank every 3 to 5 years to prevent the buildup of sludge and scum. Neglecting maintenance can lead to system failure, expensive repairs, or environmental contaminations. Another disadvantage is potential for groundwater contaminations. If a septic tank is poorly designed, installed, or maintained, it can lead to contamination of groundwater with harmful pathogens, nutrients, or other pollutants, particularly if the drain field is too close to water sources like wells or streams. Lastly, let us talk about anaerobic lagoon. An anaerobic lagoon is a large, open pond designed for the treatment of wastewater where the breakdown of organic matter occurs in the absence of oxygen. These systems are commonly used in agricultural, industrial, and municipal wastewater management, particularly for livestock manure, food processing waste, and sewage. Anaerobic lagoons operate under anaerobic oxygen-free conditions and rely on naturally occurring microorganisms to break down waste material. Anaerobic digestion in lagoons involves a sequence of biochemical processes carried out by anaerobic microorganisms, which includes hydrolysis, acetogenesis, and methanogenesis. Large organic molecules are broken down in simpler compounds like amino acids, sugars, and fatty acids by enzymes. Microorganisms further break down these compounds into volatile fatty acids, ammonia, hydrogen, and carbon dioxide. In metagenesis, a specific type of archaea then convert acetic acid, hydrogen, and carbon dioxide into methane. Methane is a primary gas produced in anaerobic lagoons, often released in the atmosphere unless captured for energy. These are the advantages of anaerobic lagoons. First, it has a low energy requirement. Anaerobic lagoons does not require mechanical aerations or constant maintenance, making them cost effective. It also produces biogas. Anaerobic lagoon produce methane which can be captured and used as a renewable energy source. One of its advantages is waste volume reduction. Through digestions, organic material is significantly reduced, lowering the volume of sludge to be handled later. It is good also in nutrient management. Lagoons can help manage nutrients like nitrogen and phosphorus, which can be valuable if further treated or used as fertilizer. However, there are also disadvantages and environmental concerns of anaerobic lagoon, one of which is its odor emissions. Anaerobic lagoons emit hydrogen sulfide and ammonia, which contribute to unpleasant odors. This can be problematic if it's especially located in populated area. It has also a greenhouse gas emission. Methane and carbon dioxide, potent greenhouse gases, are byproducts of anaerobic digestions. If biogas isn't captured, these gases can exacerbate climate change. Also, it is risk of groundwater contaminations. Without proper lining, lagoons can leach contaminants into groundwater, posing risks to the environment and public health. Also, it has a problem in sludge accumulations. Over time, sludge build up and the lagoon's bottom, reducing capacity and necessitating costly removal and disposal. Lastly, it is climate sensitive. Anaerobic processes are sensitive to temperature. Low temperatures can slow down microbial activity, reducing treatment efficiency, which can be problematic in colder climates.